So let's practice calculating pH of some strong acids and strong bases. Super simple. What makes the strong acids and bases easy is that the molarity of the solution is directly proportional to the amount of hydrogen produced. So when I see a strong acid like this, HNO3, and it dissociates fully to form hydrogen and nitrate ions, I know that if it was a 0.1 molar solution, it's going to give me 0.1 moles of hydrogen per liter. And I don't care about the nitrate. That's neither acid nor base. We'll talk about him later. I just want the concentration of the hydrogen ion. So it is the same as the molarity of the original acid, which makes these really quick and simple. So that all I have to do to calculate pH is go opposite log of that 0.1 molar solution, because that would be the concentration of hydrogen. Plug it in my calculator, done deal. pH is 1. Same thing with HCl. These are probably two of the most common strong acids. pH is opposite log of 2.0 times 10 to the negative fifth. That will be the concentration of the hydrogen ion. Now this one I'm going to plug in my calculator. Opposite log of that 2.0 times 10 to the negative fifth. I'm going to get a pH that's a decimal, but it should be close to 5. So yeah, I mean, I'm getting about like a pH of 4.7. Done. Easy. And so now the one thing that I want to make note of is that sometimes I think people incorrectly interpret the pH scale. And they want to say, like, if your pH is 1, 2, 3, you have a strong acid. When the pH is 4, 5, 6, it's a weak acid. 7's neutral, and so on. And that is so not true. Both of these are strong acids. Strong acids fully dissociate. They fully ionize. And we would know that by either having a really large Ka value, or we would say that it dissociates 100%. We could look at it as like a percent dissociation. But check this out. These are both strong acids because they fully ionize. But here I've got an HCl solution with a pH of like almost 5. And some people will mistakenly say, ugh, if the pH is 5, that's a weak acid. No, it's still strong. The HCl still fully ionizes. It's better to say that it's just really dilute. This molarity is just really small. And so, yeah, there's just not that much HCl in the solution to start with. Not all of the HC molecules present, they're going to split. There's just not that many of them. So if I don't have that many HCl molecules, I'm just not going to get that much hydrogen. And so, yeah, it's possible to have a hydrochloric acid solution with a pH of 4, 5, 6. There's 2 ways that you could get a solution that just doesn't have a lot of hydrogen. Now, obviously, one is to use a weak acid. If I have a weak acid, it just doesn't fully ionize. So, yeah, I'm not going to get a lot of hydrogen. But the other option is to use a strong acid, but just make the molarity really small. If it's a really dilute strong acid, then you also won't have a lot of hydrogen in the solution. And you could get a pH of like 4, 5, 6. So pH of strong acids, super easy. Opposite log of the molarity. Kind of similar with a strong base. A strong base is going to fully ionize. My NaOH will split apart to form sodium ions and hydroxide ions, 100%. So whatever the concentration is, and here it's like 5.0 times 10 to the negative second. I don't care about the sodium. That's not going to produce hydrogen, and it's not going to remove hydrogen. It's a spectator. But I would fully produce 5 times 10 to the negative second moles of hydroxide. right, now you've got a couple options on calculating the pH. Option 1. Let's say option 1. 2 ways to calculate the pH of a base. Well, I've got the hydroxide concentration, so it would be really easy to say POH equals opposite log of that 5.0 times 10 to the negative second, because that will be the concentration of hydroxide. I could do that. That'd be super easy. So opposite log 5 times 10 to the negative second gives me a POH of about 1.3. Then we can just use that equation, pH plus POH equals 14. Oh, yeah, this is cool. So then I just subtract. 14 minus 1.3 gives me a pH of a big fat 12.7. Just not bad. I mean, the bases require kind of an extra step, because if we're calculating pH, the H stands for hydrogen. Well, the base is producing hydroxide. And so I have to kind of do an extra step with the pH of a basic solution. But I think this is pretty manageable. It's pretty easy. Just do the POH and then subtract it from 14, and boom, you got the pH. And obviously it should be greater than 7. So yeah, like 12.7, that seems reasonable. The other option, so here's like option 2. See which one you like better. Option 2 would be to calculate the hydrogen concentration. So we could use that equation, hydrogen times hydroxide, which is what I have, equals 10 to the negative 14th. You could use that. And then I'm directly calculating the hydrogen concentration. So I could say 10 to the negative 14th divided by 5 times 10 to the negative second. That gives me 2 times 10 to the negative 13th. Oh, well, now I have the hydrogen concentration, so I can do pH right away. Opposite log of 2, or 2.0, I guess, times 10 to the negative 13th, because that is the hydrogen concentration. Now, obviously, the pH should be close to 13, but with a 2 out in front, it'll be a decimal. And guess what? It's exactly the same. pH is a big fat 12.7. So see which method you like better? They're going to lead you in the same direction. You'll get the same answer either way. Now with the second example, there's just kind of one extra step that we've got to worry about with this barium hydroxide. So let's say I think about the dissociation of barium hydroxide. Soluble base, so I'm going to get some barium ion and 2 hydroxide ions. Any soluble hydroxide will be a strong base. It'll dissociate fully, give you lots of barium and lots of hydroxide. Do you see the slight issue here? It's just that if my barium hydroxide is 0.1 molar, I don't care about the barium, but when this thing fully ionizes, I'm gonna get 0.2 molar hydroxide. No! And so we just have to be a little bit careful here that I've got this strong base, but it gives me 2 hydroxide ions. And technically for POH, I need the total hydroxide concentration. Or if I were going with option 2, same thing, I would need the total hydroxide concentration. And then I could solve for hydrogen. I don't know about you, but I think between option 1 and 2, I kind of lean toward option 1. I guess sometimes it depends on what information I'm given, but I just feel like it's easy to plug in your calculator. Or maybe first I'll calculate the POH as opposite log of 0.2. That's the concentration of hydroxide. Opposite log of 0.2 gives me about 0. I don't know, like 70. And so now all I have to do is subtract that from 14. pH plus POH equals 14. And then I got it. And so I don't think it's a hard calculation. I'd say that the pH is 13.3. I think it's easy to plug in your calculator, but for sure, either method, option 1 or option 2, they'll give you the same answer. It's just that, yeah, with the bases, no matter what, you got kind of an extra step. And that if we want pH, somehow we're going to have to deal with the fact that the base does not produce H. It does not produce hydroxide. I should say it does not produce hydrogen. Hello. It produces hydroxide. So I could either do the POH first, or I could calculate the hydrogen concentration. And all of these little equations are right in your packet.